Hey everyone, welcome back. If you're new here, I'm so glad you found your way to this quiet little corner of the universe. Get comfortable, dim the lights if you can, maybe pull a blanket a little closer. Because tonight, we are not staying on Earth. Close your eyes for just a moment. Imagine you're standing outside barefoot on cool grass, or maybe on a rooftop somewhere quiet and you tilt your head back. The sky above you is full of stars, familiar, beautiful, safe. But what if that sky wasn't this one? What if the ground beneath your feet belonged to another world entirely? And when you looked up, nothing you saw matched anything you had ever known. What if the moon was gone, replaced by two tiny moons racing in opposite directions? What if the sun above you was 3 times larger than you'd ever seen it, and the sky around it was still pitch black? What if there was no night at all, just an eternal crushing, burning orange noon that never ended? Tonight we are going to find out. We're traveling in the only way that truly matters in imagination, grounded in science through 7 worlds of our own solar system and beyond. And from each one, we are going to look up. Before we drift into the stars together, if you find something beautiful in these quiet journeys, if science told softly is the kind of thing that helps you rest and wonder, at the same time, you might like to stay a while. A gentle tap on the like button helps more people find their way here. Subscribing means the next quiet night can find you again. And the little bell, not for noise, but so you won't miss what comes next. Thank you truly. Now, let's drift. Tonight's question is one of those rare questions that seems simple on the surface and then opens up into something vast. The question is, what does the night sky look like from other planets? And I want to be honest with you about something. Before I started researching this, really researching it, sitting with the orbital mechanics, the atmospheric physics, the probe imagery, I thought I had a general sense of the answer. I thought, well, from closer planets, the sun looks bigger. From farther ones, it looks smaller, and the stars are roughly the same everywhere. The details change, but the picture is more or less familiar. I was wrong. The differences are not subtle. They are not slightly different shades of blue. They are alien in ways that stretch the imagination all the way to its edge. And some of the most extraordinary things about these other skies, the color of Mars's sunset, the way Saturn's rings arch overhead from its moon, Titan the fact that from Neptune, our own sun is barely brighter than a distant streetlight. These are not speculations. They are measurements. They are photographs. They are data transmitted back to Earth by machines we built and sent, and in some cases watched die. So, before we leave Earth's sky behind, I want to spend a little time right here, because I think it matters to understand what we're leaving. Right now, as you listen, the sky above Earth is doing something no other sky in our solar system does in quite the same way. It is dark, filled with thousands of individual stars, and hanging in it, softly glowing silver and ancient, is one moon. One. And here is something most people know, but few people truly feel. The weight of our moon is by extraordinary cosmic coincidence almost exactly the same apparent size in our sky as the sun. Not actually the same size. The sun is about 400 times larger in diameter, but the moon is also about 400 times closer. And so, they match, almost perfectly. That match is why total solar eclipses happen. That match is why from Earth's surface you can watch the moon slide in front of the sun and cover it completely, leaving only the wispy, ghostly corona glowing around the edges. No other planet in our solar system has a moon that does this. Not one. Mars has 2 moons, Phobos and Deimos, but they are small captured asteroids, lumpy and dark, nowhere near large enough to cover the sun. Jupiter has enormous moons, 4 of them larger than our own. But Jupiter is so massive that its moons orbit far enough away that from the surface they would appear as bright disks, not eclipse makers. Saturn's moon, Titan, is large and close, but Saturn's rings dominate its sky in a completely different way. Earth's eclipse geometry is, as far as we know, unique in the solar system, and we live on the planet where it happens. Have you ever stood outside during a total solar eclipse? Or watched footage of one? the moment the last sliver of sun disappears and the world goes suddenly wrongly dark and birds stop singing and the temperature drops and the corona appears like a silver crown. If you have, you already know the feeling I'm trying to describe. That disorientation, that sense of the universe doing something it shouldn't be allowed to do. That's not superstition. That's your nervous system correctly recognizing that something cosmically improbable is happening right above your head. And we get to see it from here. Now, I want to take a moment and talk about scale because scale is the foundation of everything we're going to explore tonight. One of the most common mistakes people make when thinking about the solar system is dramatically underestimating how much empty space there is between things. We see diagrams in textbooks, the sun on the left, and then Mercury, Venus, Earth, Mars, the asteroid belt, Jupiter, Saturn, Uranus, Neptune, all lined up neatly. And the planets look like they're not that far apart. Those diagrams are almost always not to scale, because if they were drawn to scale with the distances accurate, the planets would be invisible dots. The paper would have to be the size of a football field to show Jupiter and the sun would be a small orange in one end zone. Let me give you something more real. If the sun were the size of a basketball about 24 centimeters across the Earth, would be a small peppercorn about 2.5 millimeters wide, sitting 26 meters away from that basketball. The moon would be a grain of sand barely 7 centimeters from that peppercorn. And the nearest star to our sun, Proxima Centauri, would be another basketball sitting roughly 7,000 kilometers away. 7,000 kilometers on a model where the sun is a basketball. This is why the sky looks different from other planets. Not just a little different fundamentally, structurally, atmospherically different. Because distance changes everything. The sun appears smaller or larger based on how close you are. Moons appear different sizes based on their distance from the surface. The atmosphere of a planet, its thickness, its chemistry, its particles, determines what colors scatter and what colors survive. Take away the atmosphere entirely, as on Mercury, and the black of space presses right down to the horizon even at noon. And here is something worth sitting with. All of these skies, every one of them exist right now. Right now, while you are lying here listening, there is a pink-tinged sky slowly cycling over the dust plains of Mars. There is a permanent amber haze covering the methane lakes of Titan. There are 2 tiny Martian moons casting faint double shadows onto rust-colored ground. There is a place on the night side of Mercury so cold around minus 180 degrees Celsius that ice exists in permanently shadowed craters while the sunlit side cooks at 430 degrees above zero. These things are not theoretical. They have been measured, photographed, in some cases touched by the wheels of rovers and the feet of landers. I find something quietly extraordinary about that. The fact that we, a species that only figured out powered flight in 1903, has within a single human lifetime sent machines to every planet in our solar system. We have landed on Mars 7 times. We have dropped a probe into Jupiter's atmosphere. We have crash-landed on Venus, survived long enough to take readings, and transmitted them home before the heat and pressure crushed everything. We have flown past Pluto and taken photographs sharp enough to see mountains of ice and plains of frozen nitrogen. Every piece of knowledge we have about those other skies was earned. Some of it was earned at enormous cost in funding and engineering lifetimes, and in the loss of machines that scientists loved, the way you might love a piece of art you made with your own hands. The Cassini spacecraft, which orbited Saturn for 13 years and gave us our most detailed understanding of its rings and moons, was deliberately flown into Saturn's atmosphere in 2017. Because we were afraid it might crash into Enceladus or Titan and contaminate their oceans with Earth bacteria, and we didn't want to do anything that might compromise the chance those moons have of harboring life. So, we ended Cassini intentionally, and in mission control, grown scientists wept. I think that is one of the most human things I have ever heard about the space program, that we were careful enough and humble enough to sacrifice something we loved to protect something we hadn't even found yet. So as we travel tonight from Mercury to Neptune, and then out beyond to worlds we've never visited at all, I want us to carry a little of that feeling, not heavily, not sadly, just with the quiet awareness that these skies are real. They are ancient. They were there long before the first human looked up, and they will be there long after the last one does. But tonight, we are looking up. Are you ready? The first stop on our journey takes us closer to the sun than Earth has ever dared to travel, to a world so strange that time itself seems to misbehave there. A world where the sun rises, then stops, then slowly moves backward across a black noontime sky, where a single day lasts longer than a year, and where one of the most fundamental things we take for granted, the color of the sky, simply does not exist. We're going to Mercury, and I promise you, the sky there is nothing like anything you've ever imagined. If you thought Mercury was simply the smallest, fastest planet, the little one closest to the sun, that doesn't get talked about much, then what you're about to hear is going to completely change how you think about it. Mercury is one of the strangest places in the entire solar system. Not because of what it has, but because of what it does to time and light and the very concept of a sky. Standing on Mercury and looking up is not like standing anywhere else in the known universe. It is an experience so disorienting, so quietly wrong in every direction, that astronomers who first calculated what it would look like had to check their math twice, because the results didn't seem possible. And yet they are. Every detail, verified by physics, confirmed by observation, photographed by the Messenger spacecraft that orbited Mercury from 2011 to 2015, before being intentionally crashed onto its surface when it ran out of fuel. Let's go there. The first thing you would notice standing on Mercury's surface, let's say somewhere on the vast Calorus Basin, one of the largest impact craters in the solar system, roughly 1,550 kilometers across, formed about 3.9 billion years ago, when something enormous struck this small world and nearly shattered it. The first thing you would notice is the sky. It is black. Not the dark blue of Earth's pre-dawn, not the deep navy of high altitude. Black. The absolute total lightless black of open space. And it is black not at midnight, not during an eclipse, but at noon. At the moment when the sun is directly overhead and blazing with a ferocity 3 times more intense than anything we experience on Earth. The sky on Mercury is black at noon. This is one of the most counterintuitive facts in planetary science, and it trips people up constantly. The common assumption is more sunlight equals brighter sky. And on Earth that's true because Earth has an atmosphere, a thick layer of nitrogen and oxygen and tiny particles that scatter sunlight in every direction, painting the dome above us blue. That blue is not the color of space. It is the color of scattering. It is physics happening in real time above your head. Mercury has virtually no atmosphere. What little exists, a whisper-thin layer, scientists call an exosphere, is made of atoms blasted off the surface by solar wind and micrometeorite impacts. It is so thin, it cannot scatter light. It cannot hold heat. It cannot do anything that an atmosphere does. And so, sunlight on Mercury travels straight from the sun to the ground, with nothing in between to redirect it. The sky stays black. The stars are visible at noon. And the sun, this enormous blazing unfiltered sun, hangs in an absolutely dark sky, like a spotlight in an empty theater. Now, close your eyes and try to imagine that. You are standing on a plain of ancient cratered rock. The ground around you is lit so brilliantly that every shadow is sharp and deep. The temperature beneath your feet, if you were standing in sunlight, is around 430 degrees Celsius, hot enough to melt lead. And above you in a sky so black it feels like night. The sun burns 3 times larger than you've ever seen it. 3 times wider, which means roughly 9 times more surface area, 9 times more light pouring down. And yet, the sky is black. This is Mercury. This is real. But here is where it gets even stranger. And this is the part that even many science enthusiasts don't know, the part that made astronomers do a double take when the orbital calculations first came through. Mercury has the most unusual relationship with time of any planet in the solar system, not in a poetic sense, in a precise, measurable orbital mechanics sense. And it produces one of the most bizarre phenomena in astronomy, the double sunrise. To understand this, we need to talk about two different kinds of day. There is the sidereal day, how long it takes a planet to rotate once relative to the distant stars. And there is the solar day, how long it takes the sun to return to the same position in the sky as seen from the surface. On Earth, these two numbers are almost identical, 23 hours, 56 minutes versus 24 hours. The difference is tiny, caused by Earth's movement around the sun during each rotation. On Mercury, the difference is catastrophic. Mercury rotates very slowly. One full rotation takes about 58.6 Earth days, but it also orbits the sun very quickly. One full orbit takes only 88 Earth days. And these two numbers create a resonance. Mercury rotates exactly 3 times for every 2 orbits around the sun. 3 rotations, 2 orbits, every time. This is not a coincidence, it is a gravitational lock, similar to, but not the same as how our moon is locked to always show Earth the same face. This 3-2 resonance means that a solar day on Mercury from one sunrise to the next lasts approximately 176 Earth days. 176 days. Nearly 6 Earth months of continuous sunlight on the day side, followed by nearly 6 Earth months of darkness on the night side. But here is the part that breaks your brain. Mercury's orbit is not a perfect circle. It is noticeably elliptical, more oval-shaped than Earth's orbit. And this ellipse combined with a slow rotation creates a situation near Mercury's perihelion, its closest point to the Sun, where something physically impossible seeming occurs. Near perihelion, Mercury moves faster in its orbit than it rotates on its axis. The orbital motion for a brief period overtakes the rotational motion. And this means if you are standing in the right place on Mercury's surface, you would watch the sun rise in the east, then slow, then stop, then move backward westward for a period of time, then stop again, then resume its normal eastward journey across the black sky. The sun rises, goes back, then rises again. 2 sunrises from the same spot on the same day. And from another location 180 degrees opposite on the planet, you would watch the sun rise, move part way across the sky, then set, then rise again, before completing its arc. This is not a metaphor. This is not a simulation. This is orbital mechanics producing a real physical double sunrise on a world that actually exists 77 million kilometers away at its closest approach to Earth. The Messenger mission confirmed Mercury's rotation rate with extraordinary precision, and the mathematics bear it out completely. Think about what that would feel like if you could stand there and watch. The sun lifting above the horizon, pausing as if uncertain, sliding backward, and then after what might feel like an eternity of wrongness, continuing on. What would ancient humans have made of that if Mercury had an atmosphere and life had somehow found a way? What kind of myths would explain a sun that changed its mind? Now, there is a misconception I want to address directly because it comes up constantly, and it is surprisingly persistent even among people who love science. The misconception is, this Mercury is the hottest planet because it is closest to the sun. It is not. Mercury is not even the second hottest. Mercury is the 3rd hottest planet behind Venus, and depending on what metric you use, certain atmospheric layers of other bodies. Venus, despite being nearly twice as far from the sun, as Mercury maintains an average surface temperature of around 465 degrees Celsius, consistently everywhere on the planet at all times. Mercury's average temperature, by contrast, swings wildly from 430 degrees on the sunlit side to minus 180 degrees on the dark side. Why is Venus hotter atmosphere? Venus has a crushing dense atmosphere made almost entirely of carbon dioxide, with clouds of sulfuric acid creating the most extreme greenhouse effect in the solar system. Heat gets in and cannot get out. The planet traps it, stores it, bakes in it. Mercury, with its near-absent atmosphere, cannot hold heat at all. Turn away from the sun, and the temperature plummets immediately. There is nothing to retain it. This is why permanently shadowed craters near Mercury's poles, craters so deep that sunlight never reaches their floors, contain water. Ice. Ice. On the planet closest to the Sun. The Messenger spacecraft confirmed this with neutron spectrometer data in 2012. Ice sitting in the shadow a few hundred kilometers from one of the hottest surfaces in the solar system. Heat without memory, cold without night. Ice beneath a black noon sky. There is one more thing about Mercury's sky that I think is worth sitting with quietly, because it is the kind of fact that sounds like poetry, but is pure physics. From Mercury's surface, the stars are always there. Always. Whether it is the middle of the Mercurian day or the long, cold Mercurian night, the stars do not disappear. They do not wash out in a blue sky or fade into dawn light. They are present, constant, unwavering in that permanent black dome above. On Earth, we only see stars at night, not because they go away during the day, but because the scattered sunlight overwhelms them. They are there at noon, every single one of them invisible in the brightness of our own atmosphere's glow. If you were to stand inside a very deep well, looking straight up, astronomers have suggested you might just be able to see a star in daytime because the column of atmosphere above you is narrower. But in practice on Earth's surface in daylight, the stars are hidden. On Mercury, they are never hidden. You could, in theory, standing in a patch of shadow, cast by a rock formation, shielded from direct sunlight, look up at the black sky and see the stars and the sun simultaneously. The sun 3 times its familiar size, and around it, undimmed, unscattered the rest of the universe. Can you imagine what that would feel like? The sun, enormous and blazing, set against a backdrop of stars, not at night, not during an eclipse, just always. The two things we separate so completely on Earth, daylight and starlight existing together, uncompromised on a tiny airless world that has been orbiting the same star for 4.5 billion years. Mercury is old, scarred, airless, and extreme. But its sky, its black star-filled double sunrise sky, is one of the most extraordinary in the solar system. And we've only just left Earth. From Mercury, we move outward past our own planet, past Mars, to a world that should be Earth's twin. Similar in size, similar in mass, similar distance from the sun in cosmic terms. A world that for decades scientists genuinely hoped might be lush and temperate beneath its permanent cloud cover. A world we once called our sister planet. What we found when we finally looked beneath those clouds was not a sister. It was something closer to a warning. The sky above Venus is unlike anything else in the solar system, and the reason why it tells us something profound, not just about Venus, but about our own world, and how close we might be to becoming something we don't want to imagine. There is a planet in our solar system that on paper should be the most Earth-like world we know. It is almost exactly the same size as Earth, almost exactly the same mass. It formed in the same neighborhood of the solar system, from the same ancient cloud of gas and dust, at roughly the same time, about 4.5 billion years ago. For decades before we had the technology to look beneath its permanent cloud cover, scientists genuinely wondered if Venus might be warm and wet, tropical even, perhaps covered in vast, shallow oceans, perhaps teeming with life. What we found instead is the closest thing to hell that the solar system has to offer. And the sky above Venus, that thick, crushing, unbroken sky, is both the cause of the horror and one of the most scientifically important things we have ever studied. Because Venus is not just a cautionary tale about another planet, it is a mirror, and what it reflects back at us should make every one of us pay very close attention. Let's start with what you would experience if you could somehow stand on the surface of Venus. And I want to be precise here, because the numbers are the kind that the human mind tends to soften into abstraction, and they shouldn't be softened. The atmospheric pressure on Venus's surface is approximately 92 times greater than Earth's at sea level. To find an equivalent pressure on Earth, you would need to descend roughly 900 meters beneath the ocean's surface. That is nearly a kilometer underwater. The pressure at that depth is enough to crush most submarines. On Venus, that pressure exists at the surface, everywhere, all the time. The temperature is approximately 465 degrees Celsius, not just in the hottest regions, not just at noon. Everywhere on Venus, on the day side and the night side alike, at the poles and at the equator, the temperature hovers around 465 degrees. This is hotter than Mercury's sunlit surface, despite Venus being nearly twice as far from the sun. It is hot enough to melt lead, zinc, and tin, hot enough to soften aluminum. The ground itself glows faintly in infrared. The atmosphere is made primarily of carbon dioxide, about 96.5%, with clouds of sulfuric acid suspended in thick layers between roughly 45 and 70 kilometers above the surface. These clouds are so dense and so reflective that Venus seen from space is the brightest natural object in Earth's night sky after the moon. We have always been able to see Venus. Ancient civilizations tracked it carefully. The Babylonians recorded its movements as far back as 1600 BCE. The Maya built entire architectural alignments around its cycles. We called it the morning star and the evening star. And for centuries, some cultures believed it was two different objects. All that brightness, all that beauty from a distance, and beneath it something that should not exist. Here is the misconception that needs addressing clearly many people when they hear that Venus has thick cloud cover. Imagine something like an overcast day on Earth. Gray clouds, filtered light, perhaps a little gloomy, maybe some rain. The clouds of Venus are nothing like that. They do not produce rain that reaches the ground. Sulfuric acid droplets form in the upper atmosphere and fall, but they evaporate completely in the intense heat, long before reaching the surface. It rains on Venus in a sense, but the rain never lands. It dissolves back into vapor kilometers above the ground. The surface of Venus has not seen a raindrop in billions of years, and the light that filters through those clouds to the surface is not comforting overcast light. It is a dim, reddish-orange glow. Imagine standing inside a hot oven with the heating element turned up as high as it will go, and the light through the oven window is the color of deep amber. That is approximately the quality of illumination on the surface of Venus, diffuse, tinted, coming from everywhere and nowhere at once because the thick atmosphere scatters it in all directions. Soviet scientists experienced this firsthand in the most extraordinary and underappreciated chapter of space exploration history. Between 1970 and 1984, the Soviet Union's Venera program successfully landed 10 spacecraft on the surface of Venus. 10. This is a feat that is almost never discussed in proportion to its achievement. Landing on the moon is celebrated constantly and rightfully. Landing on Mars captures headlines. But landing on Venus, surviving long enough on Venus to return data, is arguably the most hostile environment any human-built machine has ever operated in. The Venera landers were engineered to survive for as long as possible under crushing pressure, extreme heat, and corrosive atmosphere. Most of them lasted between 23 minutes and 127 minutes before being destroyed. Venera 13, which landed in March 1982, survived for 127 minutes, just over 2 hours, and in that time, transmitted the first color photographs ever taken on the surface of another planet. Those photographs show flat orange-lit rock, slabs of basalt, a horizon that curves slightly inward due to the optical effects of the dense atmosphere, and above everything that amber sky glowing, featureless, pressing down. The scientists who received those images knew they were looking at photographs taken by a machine that was at the moment the images were being processed on Earth already dead. Now here is where Venus becomes not just fascinating, but genuinely important in a way that reaches directly into our own lives. Venus and Earth started with similar amounts of water. Scientists believe Venus once had liquid water on its surface, possibly for up to 2 billion years. That is long enough by some estimates for life to have had a chance. We do not know if it did. We may never know, but the water is gone now. Every last drop, evaporated into the atmosphere billions of years ago, broken apart by ultraviolet radiation from the sun and lost to space. What caused this runaway greenhouse effect? Carbon dioxide built up in the atmosphere, possibly through volcanic activity, trapping heat that could not escape. This caused temperatures to rise. Rising temperatures cause more water to evaporate. Water vapor is itself a greenhouse gas, so more vapor trapped more heat, which evaporated more water, which trapped more heat. A feedback loop that once started could not be stopped. Venus cooked itself from the inside out. The result is the sky we described, 96.5% carbon dioxide, 465 degrees, 92 atmospheres of pressure, permanent, unchanging. A world that has been locked in this state for billions of years and will remain so for billions more. Earth's atmosphere is currently about 0.04% carbon dioxide. Venus's is 96.5%. And yet the physical process greenhouse warming atmospheric feedback, the trapping of heat by gas, is the same. The difference is one of degree and time, not of kind. I am not saying Earth is becoming Venus. The distances involve the differences in solar input, Earth's active water cycle and carbon cycle. These are real moderating factors. But Venus is the clearest natural experiment we have for what happens when a greenhouse effect runs unchecked. It is a data point, a real one, sitting 38 million kilometers away, at closest approach, close enough to study, impossible to ignore. There is one more thing about Venus's sky that is quietly astonishing, and it is purely about motion. Venus rotates backward. Compared to most planets in the solar system, including Earth, Venus spins in the opposite direction. If you could stand above the solar system and look down, Earth rotates counterclockwise. Venus rotates clockwise. This means that on Venus the sun rises in the west and sets in the east. Every single day. Or rather, every single Venusian day, which lasts approximately 243 Earth days. Venus's day is longer than its year. It takes 243 Earth days to rotate once, but only 225 Earth days to complete one orbit around the sun. Except, you would never know it, because the sky is never clear enough to see the sun from the surface. The clouds are too thick. The sulfuric acid haze is too complete. You could stand on the surface of Venus for your entire life, those 127 minutes you'd have before the heat destroyed you, and never once see the sun directly. You would only ever see that diffuse amber glow, the light of a star filtered through poison, reaching you as little more than a warm, sourceless illumination. No stars at night. The clouds are too thick for that as well. No moon. Venus has no moons. No sun in the day. Just the glow, just the press of air, just the heat. And yet, and this is the detail that stays with me in the upper cloud layers of Venus, roughly 50 to 60 kilometers above the surface, conditions are actually remarkably Earth-like. Temperature around 20 to 30 degrees Celsius. Atmospheric pressure similar to Earth at sea level. Some scientists have proposed only partly in jest that the most habitable place in the entire inner solar system, other than Earth's surface, might be the upper atmosphere of Venus. Floating cities held aloft by breathable air in a sea of sulfuric acid clouds above a world that cannot be touched. The sky of Venus viewed from above those clouds is actually rather beautiful, vast, bright white and yellow, lit by a sun that appears normal-sized from there. Not the crushing giant it was, on Mercury, not yet the diminished dot it becomes at the outer planets. From the cloud tops of Venus, the sun rises in the west, moves slowly across the sky over the course of months, and sets in the east, slowly, steadily. The slowest sunrise in the solar system, a backward sun, rising in the wrong direction, moving at geological pace, across a sky made of acid. That is Venus. The next world on our journey is one we know far better. We have sent more spacecraft there than to any other planet. We have landed rovers on its surface and listened to its wind. We have photographed its sunsets and watched its two small moons rise and set. And yet, even here, the sky above this world holds surprises that most people have never heard about, including one color that appears at exactly the wrong moment and only lasts for a few quiet minutes. We're heading to Mars, and the sky there is nothing like you'd expect. On June 20th, 2015, NASA's Curiosity rover was sitting quietly on the surface of Mars, a world 225 million kilometers from Earth at that moment, and it pointed its cameras at the horizon just as the sun was beginning to set. What it captured was one of the most unexpectedly beautiful photographs ever taken on another planet. The sky around the sinking sun turned blue, a soft, pale, unmistakable blue, the color we associate with clear Earth skies, with open water, with morning. But this was Mars, and on Mars that blue appears only at sunset and sunrise, lasting just a few quiet minutes, before the rest of the sky reasserts its true color. A color that is the exact opposite of Earth. A sky that is in its ordinary hours pink. Mars gives us everything in reverse. The blue comes at dusk. The warmth comes from rust. And the night has two moons moving in directions that should not make sense. Let's go to Mars, and let's look up. If Mars has an atmosphere, this is the first thing worth establishing clearly, because many people assume it is as airless as Mercury. It is not, but it is close. The Martian atmosphere is about 95% carbon dioxide, similar in composition to Venus, but incomparably thinner. The surface pressure on Mars is less than 1% of Earth's at sea level. You could not breathe it. You could not survive in it without a pressure suit. But it is enough, just barely enough, to do something to light. The atmosphere of Mars is loaded with fine dust particles. Iron oxide dust, rust, essentially. The same mineral that gives Mars its characteristic red-orange color on the ground also floats suspended in the thin air. And it is this dust that governs everything about the Martian sky. During calm periods, the dust settles somewhat, and the sky takes on a pinkish tan color, almost salmon, almost butterscotch. During dust storms, which on Mars can grow to cover the entire planet, global storms that last for months, the sky darkens to a deep brownish orange and sunlight at the surface drops dramatically. The Opportunity rover, which landed on Mars in January 2004 and was designed to operate for 90 days, ended up surviving for nearly 15 years until June 2018, when a planet-wide dust storm so severe that it blocked out almost all sunlight finally drained its solar panels completely. The last signal from Opportunity was received on June 10th, 2018, after 511 Martian days of operation, after traveling 45.16 kilometers across the Martian surface. The mission team sent one final command into the dark, knowing they would not hear back. They played Billie Holiday's "I'll Be Seeing You," and then they let go. A rover that outlived its expected lifespan by 60 times finally stopped not by mechanical failure or age, but by a sky that went dark. That is how powerful Martian dust storms are. Now here is the detail that surprises almost everyone when they first encounter it. That blue sky at sunset. Why does it happen? And why is it the reverse of Earth? On Earth, we experience blue skies during the day and reddish-orange skies at sunset, for the same underlying reason, the scattering of light. When sunlight passes through atmosphere, different wavelengths of light scatter differently. Short wavelengths, blues and violets, scatter more easily off gas molecules. Long wavelengths, reds and oranges, pass through more directly. At midday, when sunlight comes straight down through the least amount of atmosphere, the scattered blue dominates and we see a blue sky. At sunset, when sunlight travels through a much longer path of atmosphere to reach our eyes, most of the blue has scattered away, and what reaches us is predominantly red and orange, hence the warm colors of Earth's sunsets. On Mars, the process is reversed, not because the physics are different, but because the scatterer is different. Instead of gas molecules, it is dust particles. And dust particles are much larger than gas molecules. Larger particles scatter long wavelengths, reds and oranges, more efficiently. So, during the Martian daytime, the red scattering dust particles fill the sky with pinkish red light, giving Mars its characteristic daytime hue. But at sunset, when sunlight angles through a longer path, and the larger dust particles have done their scattering, the shorter blue wavelengths, which pass more cleanly through dust than red, does begin to dominate near the sun on the horizon. And for a brief window of minutes, the sky around the setting sun glows blue. Same physics. Opposite result. Because the atmosphere is made of different stuff. Think about what this means more broadly, and I want to pause here and invite you to sit with this thought for a moment. The color of a sky is not a fixed property of a planet. It is an emergent property of the interaction between starlight and atmosphere. Change the atmosphere, and you change the color. The blue of Earth's sky is not the color of sky. It is the color of our particular sky with our particular mix of gases lit by our particular sun. Every world with an atmosphere has its own sky color. And as we'll see tonight, some of them are colors we do not have good words for. But the sky color is only the beginning of what makes Mars extraordinary to observe from the surface. The sun itself looks different. From Mars, the sun is smaller. Not dramatically, Mars orbits about 1.5 times farther from the sun than Earth does. So the sun appears about 2/3 the angular diameter it does from Earth. It is still clearly a disk, still the brightest object in the sky by enormous margin. But there is something about a slightly smaller sun that changes the emotional quality of the light. Photographs taken by Mars rovers, particularly the panoramic images from Spirit, Opportunity, and Curiosity, show a landscape lit with a quality that feels almost melancholy. The light is correct but slightly wan, slightly withdrawn, like afternoon light on an overcast autumn day on Earth. Sufficient but not generous. And the shadows. On Earth, shadows have soft edges because our atmosphere scatters light in all directions, filling in the darkness from multiple angles. On Mars, with its thin atmosphere, shadows are sharper. Not as sharp as Mercury's, there is still some scattering, but noticeably more defined than Earth's. The landscape in full Martian daylight is a study in sharp contrasts, vivid orange rock and clean-edge black shadow. Then the night comes, and the night on Mars is where things become genuinely strange. Mars has two moons, Phobos and Deimos. And they are nothing like our moon in size and origin and behavior or in how they appear in the Martian sky. Phobos, the larger of the two, is not large. It measures roughly 27 kilometers at its longest dimension. It is not spherical. It is lumpy potato-shaped, heavily cratered, with a massive impact crater called Stickney on one end that is nearly half the moon's total diameter. The impact that created Stickney very nearly shattered Phobos entirely. You can see the fracture lines running across the surface. It is a moon held together barely by its own weak gravity and a mutual stubbornness with destruction. Phobos orbits Mars at an altitude of only 6,000 kilometers, closer to the surface of its planet than any other moon in the solar system. By comparison, our moon orbits at about 384,000 kilometers. Phobos is so close that it moves faster than Mars rotates. It completes a full orbit in just 7 hours and 39 minutes. This means that from the Martian surface, Phobos does something no moon, and our sky does. It rises in the west and sets in the east, the opposite of every other rising and setting we know, and it crosses the entire sky from horizon to horizon in roughly 4 to 5 hours. You can watch it move visibly steadily crossing the stars, like a bright point of light that has somewhere urgent to be. On some nights, Phobos rises and sets twice before the Martian night is over. Deimos, the smaller moon just 15 kilometers across, orbits much farther out at about 23,000 kilometers and moves much more slowly. From the surface, Deimos looks barely larger than a bright star. You might mistake it for Venus if you didn't know better. It takes about 30 hours to cross the sky, and it moves in the correct direction east to west, like Earth's moon, because it orbits slower than Mars rotates. So, On a clear Martian night, you might watch Phobos rising in the west, racing eastward, while Deimos drifts slowly westward overhead. Two moons, moving in opposite directions, both so small they cast almost no useful light. A night on Mars is genuinely dark in a way that Earth nights rarely are. Our moon is bright enough to cast shadows and read by in principle. Phobos at its brightest provides roughly 1% of the light our moon gives. Martian nights are dark and cold. Surface temperatures at night on Mars drop to around minus 73 degrees Celsius in the equatorial regions and can plunge to minus 125 degrees near the poles in winter. The thin atmosphere cannot hold the day's heat. The moment the sun sets, Mars begins to freeze. There is one more thing about the Martian sky that deserves mention, something that brings the entire picture together in a quietly moving way. We have heard the wind on Mars. NASA's InSight lander, which touched down on Mars in November 2018, carried a seismometer sensitive enough to detect not just Marsquakes, but also the passage of wind across its sensors. In December 2018, it recorded the first sounds ever captured on another planet. Low, deep vibrations. The sound of Martian wind moving thin air across a cold landscape under a pink sky. It does not sound like Earth wind. It is slower, lower, more diffuse, like the memory of wind rather than wind itself. Scientists described it as haunting, and I think it is. The idea that we have heard another world, not seen it through a telescope, not calculated it from orbital data, but actually heard it, pressed our instruments against it, and then listened, that crosses some line from science into something that feels almost intimate. Mars is cold and dry and thin-aired and possibly dead as far as life is concerned, though we have not yet proven that either way. But it has a sky that turns blue at sunset. It has two small moons moving in opposite directions. It has wind. And somewhere in its frozen soil, there may be answers to questions about life in the universe that we have been asking for, as long as we have been capable of asking anything at all. We've now moved from the innermost planet to the edge of the inner solar system, and the next stop takes us somewhere that changes the scale of everything we've discussed so far. The planet we're heading to is so massive it could fit every other planet in our solar system inside it, with room to spare. Its storms have been raging for centuries. And from within its cloud layers, if you could somehow stand there on a world that has no surface to stand on, the sky is the most violent, the most layered, and in some ways the most breathtaking in the entire solar system. We're going to Jupiter. And on Jupiter, the sky is not something you look at. It is something you fall through. Imagine falling, not falling towards something, not toward a floor, not toward water, not toward safety of any kind. Just falling endlessly through layers of cloud that grow thicker and hotter and more crushing with every kilometer. Above you, the sky you entered is already gone, sealed over by the next layer of atmosphere. Below you, there is no ground coming. There never will be. You will fall until the pressure of the air itself becomes so immense that it stops you not by catching you, but by destroying you first. And all around you in every direction, the sky is moving. Bands of cloud in cream and amber and rust orange moving at hundreds of kilometers per hour in alternating directions east and west, like a planet-sized engine running on nothing but its own ancient momentum. This is Jupiter, the largest world in our solar system, a place so vast that every other planet, every moon, every asteroid, every comet in the entire solar system could fit inside it, and there would still be room left over. Not just barely room, significant room. Jupiter is not just the biggest planet. It is in a very real sense a different category of thing. And its sky, the sky of Jupiter, is the most dynamic, the most layered, the most violent sky in the solar system, possibly in the known universe within the worlds we have studied. Let's fall into it. First, let us settle the misconception that trips up almost everyone at some point, even people who have been interested in astronomy for years. Jupiter does not have a surface. Not in the way we mean when we use that word. There is no ground, no rock, no place where the atmosphere ends and something solid begins. What Jupiter has is a continuous gradient from the thin outer wisps of its uppermost cloud layers through increasingly dense and hot layers of gas into regions where hydrogen is compressed so extremely that it begins to behave like a liquid, and then into a region of liquid metallic hydrogen, a state of matter that does not exist anywhere on Earth under natural conditions, and possibly at the very core. A dense region of rock and ice that is itself nothing like any surface we have ever stood on, but you could never reach it. Long before you arrived, the pressure and temperature would have ended you. The Galileo probe found this out in the most direct way possible. In December 1995, NASA's Galileo spacecraft released a small probe about 340 kilograms, roughly the size of a large refrigerator, into Jupiter's atmosphere. The probe was built to withstand extraordinary conditions. It entered the atmosphere at 47 kilometers per second, generating temperatures of around 15,500 degrees Celsius, from aerodynamic heating hotter than the surface of the sun. It survived that. It deployed a parachute. It descended. And for 57 minutes and 36 seconds, it transmitted data back through the Galileo orbiter to Earth temperature, pressure, wind speed, atmospheric composition. Then the pressure and heat became too much, and the probe was crushed and vaporized. It had reached a depth of roughly 200 kilometers below the cloud tops. It had barely scratched the surface of a planet that has no surface. Those 57 minutes of data rewrote much of what we thought we knew about Jupiter's atmosphere. The probe found that wind speeds were higher than expected, around 530 kilometers per hour. It found less water vapor than models had predicted. It found that Jupiter's atmosphere is more complex, more layered, more turbulent than we had assumed from afar. 57 minutes. A machine we built and sent across 600 million kilometers of space survived entry hotter than the sun and gave us less than 1 hour before the planet took it. So, when we talk about the sky of Jupiter, we are talking about the atmosphere itself, because on Jupiter, the sky is everything. There is no ground to stand on and look up from. Instead, let us think about what it would look like from within those upper cloud layers, where the Galileo probe spent its brief operational life. The clouds of Jupiter are arranged in bands, the light-colored zones, and the darker belts that we can see so clearly from Earth through even a modest telescope. These bands are driven by Jupiter's extraordinarily fast rotation. Despite being 11 times wider than Earth, Jupiter rotates once every 9 hours and 56 minutes, faster than any other planet in the solar system. This rapid spin stretches its weather systems into horizontal bands that wrap all the way around the planet, stable over time scales of decades or longer. The colors of those bands come from their chemistry. The lighter zones are regions where gas is rising, cooling, and condensing into white ammonia ice clouds. The darker belts are where gas is sinking, and deeper, warmer, chemically richer layers are exposed, bringing up compounds of sulfur, phosphorus, and complex organic molecules whose exact chemistry we still do not fully understand. The precise source of Jupiter's famous reddish-brown color remains one of the genuinely open questions in planetary science. We know the pigments are there. We are not entirely sure what makes them. Within those cloud layers, from the vantage of the Galileo probe's descent, the sky above would have appeared as a progressively thickening ceiling. The cloud deck from which you entered now closed over you, glowing with diffuse light from the sun above. The sun from Jupiter is about 5 times farther away than it is from Earth, so it appears about 5 times smaller in the sky, still a disk, still unmistakably the sun, but diminished. The light at Jupiter's cloud tops is roughly 27 times dimmer than sunlight on Earth, enough to see by, not enough to feel warm. Around you, the winds. Moving in great parallel rivers, the equatorial jets of Jupiter blow at velocities that dwarf anything on Earth. The fastest sustained winds in Earth's atmosphere in the jet stream at high altitude reach perhaps 400 kilometers per hour in exceptional circumstances. Jupiter's equatorial winds move at around 640 kilometers per hour, sustained, permanent, ancient. They have been blowing at essentially the same speed and in the same direction for as long as we have been able to observe them. The Great Red Spot, the most famous feature in Jupiter's atmosphere, a storm system larger than the entire Earth, has been observed continuously since at least 1831. And historical records suggest something like it may have been seen as early as 1665. It has been rotating counterclockwise for somewhere between 190 and 350 years. A single storm older than the United States, larger than our entire planet, turning without pause. And yet, the Great Red Spot has been shrinking. In the early 19th century, it was estimated to be around 40,000 kilometers wide. By the time a Voyager's flyby in 1979, it was 23,000 kilometers across. By 2023, it had shrunk to roughly 13,000 kilometers. Still enormous, still larger than Earth, but measurably consistently, mysteriously smaller with each passing decade. We do not fully know why. We do not know if it will eventually disappear entirely, or stabilize, or something else entirely. The largest storm in the solar system is slowly, quietly doing something we cannot yet predict. Now here's the aspect of Jupiter's sky that I find most quietly astonishing. And it has nothing to do with Jupiter itself, but with what you would see when you looked away from it. Jupiter has 95 known moons as of our most recent count. 95. The four largest, Io, Europa, Ganymede, and Callisto, were discovered by Galileo Galilei in January 1610, and they are known as the Galilean moons in his honor. They are not small. Ganymede, the largest, is bigger than the planet Mercury. Europa is roughly the size of Earth's moon. Io is slightly larger than our moon. Callisto is almost as large as Mercury. From Jupiter's cloud tops, these moons would be visible as disks, not points of light, but actual disks like small moons, but without the softness our moon has. Io, orbiting closest, would appear about the same angular size as our moon does from Earth. Ganymede, orbiting farther out, would appear somewhat smaller. All four would be visible simultaneously in different positions, tracking their orbits around Jupiter at different speeds. Io completes an orbit in about 1.8 Earth days. Europa takes about 3.5 days. Ganymede takes 7 days. Callisto takes about 17 days. And they are locked in a gravitational resonance with each other for every one orbit Ganymede completes. Europa completes 2, and Io completes 4. Exactly. Every time. A gravitational harmony that has been maintained for billions of years. This resonance has enormous consequences. The gravitational tugging between these moons, particularly the relentless pulling of Jupiter, combined with the orbital resonance, generates tidal heating inside Io, so extreme that Io is the most volcanically active body in the entire solar system, more volcanically active than Earth. Its surface is covered in sulfur yellow and orange and white and black, constantly being resurfaced by hundreds of active volcanoes. Some of Io's volcanic plumes shoot material 500 kilometers above the surface. From Jupiter's cloud layers, you might be able to see Io's volcanoes glowing against its surface, a tiny disk of sulfurous yellow, spotted with glowing orange eruptions. Europa, meanwhile, hides something extraordinary beneath a surface of cracked, smooth ice, a liquid water ocean, estimated to contain more water than all of Earth's oceans, combined kept liquid by tidal heating from the same gravitational forces that make Io so volcanic. The cracks in Europa's ice surface are visible in our telescope. In spacecraft images, they look like a cracked eggshell, reddish-brown material welling up from below along the fracture lines. Something is happening under that ice. We do not know what. The possibility that it could be life has been taken seriously enough that NASA launched the Europa Clipper mission in October 2024, now en route to Jupiter, designed to study Europa in extraordinary detail. I want to pause here for a moment and invite you to consider something. From Jupiter's cloud tops, you would be surrounded by a sky of constant violent wind, with the sun reduced to a bright but distant disk, 4 large moons visible as actual disks of varied color and surface detail. and 91 additional smaller moons scattered at various distances. And below you, or around you, or in every direction, depending on where in the atmosphere, you were nothing but more sky growing hotter and heavier and darker as it descended toward a core you could never reach. There is no horizon on Jupiter in the way we mean it. The planet is so large that its curvature at cloud top level is barely perceptible. The bands of cloud extend to the limits of vision in every direction. The scale simply does not register in human terms. We are built for Earth. We can understand a hill and a valley and a coastline. Jupiter is not a place. It is a condition. And yet Galileo saw those 4 moons with a telescope he built himself, with lenses ground by hand in 1610. He watched them move night after night. He realized they were orbiting Jupiter, not Earth. And in doing so, he delivered one of the most important blows to the Earth-centered model of the universe that had dominated human thought for over 1,000 years. 4 small points of light moving around another world, proof that not everything orbited Earth, that Earth was not, in fact, the center of everything. We have been building on that realization ever since. What we leave behind as we move outward from Jupiter is scale. Not entirely, but the scale of what awaits us next is different in character. Where Jupiter overwhelms through mass and violence and perpetual storm, the next world overwhelms through something quieter, something more geometric, something that, when you see it for the first time, even in a photograph, even on a screen, produces a sensation that is almost impossible to describe. A feeling that the universe has done something it was not supposed to be able to do. Something that looks in every photograph ever taken of it exactly like a painting. We are heading to Saturn, and the first thing you need to understand about Saturn's sky is that the rings are not something you see in it. The rings are the sky. There is a photograph taken by the Cassini spacecraft in 2013 that stopped people in their tracks when it was released. Not scientists, everyone. It circulated across the internet quietly without fanfare, and people kept sharing it because they could not quite believe it was real. In the photograph, Saturn hangs in the darkness lit from behind by the sun, its rings spreading outward in concentric arcs of gold and amber and silver. And there in the lower right of the frame, barely visible against the darkness between the rings, a tiny pale dot. A pale blue dot. Earth. Our entire world captured as a point of light smaller than a period at the end of a sentence photographed from 1.4 billion kilometers away. The photograph is called The Day the Earth Smiled, because on that day, July 19th, 2013, NASA had announced in advance that Cassini would be photographing Earth, and across the world, people went outside at the designated time and looked up at Saturn, knowing that a spacecraft there was looking back. For the first time in history, humanity posed for a portrait from another planet and smiled. That is the kind of thing Saturn does to people, even from a distance, even in a photograph. And standing beneath its rings from the surface of one of its moons, the effect is something no human language has yet developed adequate words for. Let us go to Titan first. Because Titan is in many ways the most extraordinary moon in the solar system, and standing on its surface and looking up gives an experience unlike anything else we will encounter on this entire journey. Titan is Saturn's largest moon. It is larger than the planet Mercury. It is the only moon in the solar system with a dense atmosphere, thick enough to support weather, thick enough to produce rain, thick enough that you could walk on its surface without a pressure suit, though you would need an oxygen supply and protection from the cold. The surface pressure on Titan is about 1.5 times Earth's at sea level, actually slightly more comfortable in pressure terms than Earth's. The temperature is approximately minus 179 degrees Celsius. And the rain that falls from Titan's clouds is not water. It is liquid methane. The Huygens probe released by Cassini and named for the Dutch astronomer Christian Huygens, who discovered Titan in 1655, descended through Titan's atmosphere on January 14th, 2005. It was the first soft landing ever achieved in the outer solar system. For 2 hours and 27 minutes, it fell through Titan's orange haze, taking photographs, measuring temperature and pressure, and wind recording sounds. It landed on a plain of rounded pebbles, ice pebbles smoothed by flowing liquid methane, the way river stones on Earth are smoothed by water. The ground was soft and slightly yielding, like wet sand. The temperature was minus 179 degrees. The sky above was orange, not a pale orange. A deep, thick, hazy amber orange-like, looking through a bottle of old honey toward a light source. The haze on Titan is composed of complex organic molecules. Tholen scientists call them produced when methane and nitrogen in the upper atmosphere are broken apart by ultraviolet radiation and recombine into more complex chains. These tholins rain gently down through the atmosphere, painting every surface orange, giving the air its characteristic color. They are among the most complex organic molecules in the solar system. Some scientists believe that the chemistry happening in Titan's atmosphere is a distant cousin of the chemistry that, on early Earth, may have eventually produced the first biological molecules. Whether that parallel leads anywhere significant on Titan, whether something stirs in those methane lakes, we do not know. From Titan's surface, the sun is not visible. The haze is too thick. There is light, a diffuse sourceless orange illumination, slightly brighter in the direction of the sun, but without a clear disk. It is the quality of light you might find deep inside a thick fog on an overcast afternoon on Earth. Except the fog is orange and the temperature is within a few degrees of absolute zero for liquid methane. The light is sufficient. You could see by it, but you would never find shadow and you would never see a star. And yet, looking up through that haze at the right moment in the right direction, you might see something vast and ghostly looming above. Not clearly, not sharply, but present. The rings of Saturn seen through Titan's thick atmosphere would appear as a diffuse arc across the sky, a faint brightening, a suggestion of structure, enormous and indistinct, like a rainbow made of something more solid. Saturn itself would appear as a large glowing disk, about 11 times the angular size of our full moon, as seen from Earth, pale and ringed, hanging in the orange. It would be unmistakable, even through the haze, even blurred by atmosphere. The sight of a ringed planet filling a significant portion of your sky is not something the eye would mistake for anything else. Now let us move to a different moon one with a cleaner view. Enceladus, a small icy world just 504 kilometers in diameter, orbiting Saturn much closer than Titan does. Enceladus has an almost unbelievably smooth white reflective surface. It is one of the most reflective objects in the solar system, bouncing back nearly all of the light that reaches it. It reflects about 99% of incoming sunlight, which makes it extraordinarily bright, but also extremely cold, because very little solar energy is absorbed. Surface temperatures hover around minus 198 degrees Celsius. From the surface of Enceladus, the view of Saturn would be overwhelming. Enceladus orbits about 238,000 kilometers from Saturn's center, close enough that Saturn fills a huge portion of the sky. The ringed planet would appear roughly 10 times the angular diameter of our full moon, as seen from Earth. At certain orbital positions, the rings would appear nearly edge-on, a thin, brilliant line of light arcing across the sky. At other positions, as Enceladus moved in its orbit, the rings would open up, tilted toward you. Their full structure revealed the Cassini division, that dark gap between the A ring and B ring, visible as a distinct dark band within the brilliant arc. The Cassini division, incidentally, is not actually empty. It appears dark because it contains fewer ring particles than the dense main rings on either side, but it still contains material. The division was cleared out by an orbital resonance with Saturn's moon. Mimas, every particle that ended up in that zone got pulled into a 2-to-1 resonance with Mimas, meaning it orbited Saturn exactly twice for every one orbit of Mimas, and the gravitational tugging over billions of years cleared the region. The same gravitational resonance mechanics that organizes Jupiter's moons, that drives Io's volcanism here, sculpts the very structure of Saturn's rings into visible bands and gaps. And here is the detail about Enceladus that makes it, in the view of many astrobiologists, the single most exciting destination in the solar system for the search for life. At the south pole of Enceladus, there are fissures in the ice cracks in the surface from which enormous geysers erupt, continuously shooting water vapor and ice particles hundreds of kilometers into space. These plumes were discovered by Cassini in 2005 and confirmed in extraordinary detail over subsequent years. The material ejected by these geysers actually feeds Saturn's E-ring, the outermost. And most diffuse of Saturn's main rings is made in significant part from the water and ice sprayed into space by tiny Enceladus. And that water, when Cassini flew directly through those plumes in 2008 and 2015, contains something extraordinary. Complex organic molecules, molecular hydrogen, silica particles that could only have formed through water-rock interactions at temperatures above 90 degrees Celsius. Carbon dioxide, methane, and critically salts, sodium chloride, table salt. The presence of salts and silica in plumes erupting from the south pole of an icy moon tells us that liquid water is in contact with rocky material at the base of an ocean beneath the ice, creating hydrothermal conditions. The same kind of hydrothermal conditions that exist at the bottom of Earth's oceans around deep-sea vents, where some of the most diverse ecosystems on our planet exist in complete darkness, fed entirely by chemical energy rather than sunlight. Standing on Enceladus, you could watch those plumes erupting from the south polar region, great white columns rising kilometers above the surface, backlit by the distant sun, with Saturn and its rings hanging above everything. Water from a hidden ocean shot into space, catching sunlight glittering. An active geological, possibly habitable world, small enough to drive across in a few hours, orbiting a planet so beautiful it looks like a painting. Here is the misconception I want to address about Saturn's rings, because it is one of the most persistent in popular astronomy. Many people imagine the rings as a solid disk, like a vinyl record, flat and smooth and opaque. They are not. Saturn's rings are made of countless individual particles ranging from tiny dust grains to chunks of ice and rock the size of houses, each orbiting Saturn independently, like billions of tiny moons. The rings are extraordinarily thin relative to their width. The main rings extend outward about 280,000 kilometers from Saturn, roughly 70% of the distance from Earth to our moon, and yet they are on average only about 10 to 100 meters thick. Some regions are just a few meters. The rings are so thin relative to their width that if you scaled them to the size of a sheet of paper, that paper would be far thinner than a single atom. The rings span continent-sized distances and are paper thin. If the rings were the width of a football field, 90 meters, they would be thinner than the finest human hair. And they are temporary, not on human timescales, but on astronomical ones. The particles in Saturn's rings gradually spiral inward, pulled by Saturn's gravity and dragged by the planet's magnetic field. Scientists estimate that Saturn's rings in their current form are somewhere between 10 and 100 million years old, not 4.5 billion like Saturn itself. They may have formed from the breakup of a moon or a captured comet, and they will be gone in another 100 million years or so, raining down into Saturn's atmosphere. 100 million years sounds like forever. But in the 4.5 billion year story of the solar system, it is a brief moment. We live at a time when Saturn has rings. Our distant descendants may not. We are right now living in Saturn's ring era, and we can look up and see them. I find that thought quietly beautiful and quietly urgent. The rings of Saturn are not permanent. They are not a given. They are a coincidence of timing, and we are inside that coincidence. Every image Cassini ever sent back, every ring photograph, every glimpse of Titan's orange haze and Enceladus's white geysers, all of that was observation of something temporary, something that will one day be gone. That is not sad, or rather it is a little, but it is also something else. It is a reminder that the universe does not hold its beauty for long. Things form and dissolve and reform as something different, Saturn had no rings before, and Saturn will have no rings again. But right now, for this brief window in cosmic time, they are there. Vast and thin and impossible looking. And we happened to arrive at a moment when we could see them. The universe arranged something beautiful. We were here to notice. From Saturn's golden amber and its ring-marked sky, we now move outward into colder territory, to two planets so strange in their orientation and their distance that the very nature of light and time and what it means to have a season becomes something almost philosophical. Two ice giants rolling through the dark, each with a sky that makes everything we have seen so far feel almost ordinary. We are heading to Uranus and Neptune. And out there at the frozen edge of our solar family, the sky tells a story about solitude that no other world in our system can quite match. There is a planet in our solar system that is currently experiencing summer. It has been summer there for decades, and it will remain summer for decades more. But this summer brings no warmth, no long evenings, no softening of light. This summer means the sun never sets. It circles endlessly above the same hemisphere day after day, year after year, for 42 Earth years at a stretch. And then the light disappears entirely. For the next 42 years, nothing but darkness. No dawn, no afternoon. Just a complete, total, unbroken polar night that lasts longer than most human lives. This is Uranus, a planet so strange in its orientation that the concepts of day and night, of season and sky, have to be completely reinvented to describe it. A world that rolls through space on its side, its axis tilted not slightly, not moderately, but at 98 degrees to its orbital plane, almost perfectly sideways, as if something enormous struck it billions of years ago and knocked it over, and it has been tumbling through the solar system in that peculiar sideways roll ever since. And next to it, in the cold dark beyond Neptune, the windiest planet in the solar system, a world of storms that make Jupiter's great red spot look almost gentle, a world so far from the sun that its discovery had to be predicted mathematically before anyone could find it with a telescope. Two ice giants rolling through the outermost dark, and their skies, their cold, distant, storm-torn skies, are the last inhabited territory before the solar system gives way to the emptiness between stars. Let us start with color, because it is the first thing anyone notices about both worlds. Uranus and Neptune are both blue, but they are not the same blue. Uranus is a pale, even almost featureless blue-green, the color of shallow Caribbean water on a calm day, or perhaps of old glass. Neptune is a deeper, richer, more saturated blue, vivid, intense, almost electric, like the color of deep ocean water, where sunlight barely penetrates. Both colors come from the same source. Methane in their upper atmospheres absorbs red wavelengths of sunlight and reflects blue. But Neptune's blue is deeper, and scientists are not entirely certain why. The two planets have similar methane concentrations in their upper atmospheres. Something else, some additional absorbing agent we have not yet identified, appears to be darkening Uranus and making Neptune comparatively brilliant. As of the most recent research available, this remains an open question. From Earth, Uranus is just barely visible to the naked eye under ideal conditions, magnitude 5.7, right at the threshold of human vision. It was actually observed and recorded several times before it was recognized as a planet. John Flamsteed, the first astronomer, Royal of England, recorded it in 1690 as a star and catalogued it as 34 Tauri. 17 additional observations of this apparent star were recorded before William Herschel, observing on the night of March 13, 1781, from his garden in Bath. England noticed that one of the objects in his telescope showed a disk. Stars at any magnification remain points of light. This object grew. It was a planet. The first planet to be discovered with a telescope. The first planet discovered in recorded human history. Herschel initially wanted to name it Georgium Sidus, George's star, after King George III, his patron. The scientific community, understandably, was not enthusiastic about naming a planet after a living monarch. The name Uranus, following the tradition of Roman and Greek mythology after the primordial sky deity, father of Saturn, was eventually adopted, proposed by the German astronomer Johann Bode. It took decades for the name to be universally accepted. Some British sailors and astronomers were apparently still calling it the Georgian planet well into the 19th century. Now, let us do something that I think gives a real sense of how remote we have traveled. I want you to think about light. Sunlight leaves the surface of the sun and crosses space at approximately 300,000 kilometers per second. It reaches Earth in about 8 minutes and 20 seconds. It reaches Mars in about 12 to 21 minutes, depending on orbital position. It reaches Jupiter in about 43 minutes, Saturn in about 79 minutes, and Uranus, distant sideways, pale blue-green Uranus, in about 2 hours and 40 minutes. Neptune, the outermost planet, receives sunlight that has been traveling for approximately 4 hours and 10 minutes. By the time those photons reach Neptune, they have crossed nearly 4.5 billion kilometers, and they arrive weakened to the point that sunlight on Neptune's cloud tops is about 900 times dimmer than sunlight on Earth. In practical terms, standing in Neptune's upper atmosphere, the sun would appear as an intensely bright star, a star bright enough to cast faint shadows, possibly bright enough to read by in ideal conditions, but nothing like the warm radiance we experience on a clear day. It would look like a brilliant point in a dark sky surrounded by other stars that are barely dimmer. You could not feel its warmth. The sun would give Neptune's cloud tops temperatures around minus 218 degrees Celsius, cold enough that nitrogen, a gas that makes up 78% of Earth's breathable air, would be frozen solid, cold enough that methane exists in complex states cycling between atmosphere and frozen surface in ways we are still working to understand. And yet, Neptune is warmer than it should be, significantly warmer. Scientists calculate that Neptune receives so little solar energy that its internal temperature should be considerably colder than it actually is. Neptune radiates about 6 times more energy into space than it receives from the sun. Something inside Neptune, some process of slow gravitational contraction or residual heat from formation or some mechanism we have not yet identified, is generating heat from within. Neptune keeps itself warm quietly in the cold beyond the reach of sunlight. Uranus intriguingly does not. Uranus radiates almost exactly the same amount of energy as it receives no significant internal heat source that we can detect. Why one ice giant has internal heat and the other apparently does not is one of the genuinely puzzling open questions of planetary science. They are similar in size, similar in composition. They formed in the same region of the early solar system, and yet their thermal behavior is completely different. Now, the sky of Uranus, and what makes it unique in ways that go far beyond its sideways tilt. The tilt of Uranus, 98 degrees, means that its poles take turns facing the sun directly. For approximately 42 Earth years, the North Pole is in sunlight. Then, as Uranus completes half an orbit around the sun, which takes 84 Earth years for one full orbit, the South Pole comes into sunlight for the next 42 years. During these polar summers, the sun circles endlessly above the same pole, never rising or setting, just tracking in wide circles above the horizon. Meanwhile, the opposite hemisphere is locked in perpetual darkness. And here is the detail that makes this more than just an interesting astronomical fact. The equatorial regions of Uranus during the solstice periods experience something extraordinary. From near the equator, the sun would appear to move in a path that stays very close to the horizon, circling around it, rising only slightly above and dipping only slightly below, like a slow, continuous sunset and sunrise that never quite decides which one it is, for years at a time. What does this do to the sky? Uranus has an atmosphere of hydrogen, helium, and methane. Its upper cloud layers are composed of methane ice crystals, which scatter light in the blue-green range, hence its color. The sky from within those cloud layers would be that characteristic blue-green, with the sun reduced to a brilliant but tiny disk. And because of the extreme axial tilt, the sun's position in the sky changes so slowly on such enormous time scales that weather patterns on Uranus are influenced by seasons that last decades. When Voyager 2 flew past Uranus in January 1986, the only spacecraft ever to visit this world, spending just a few hours in its vicinity, it found a surprisingly featureless atmosphere. Almost no visible cloud structure, no storms, no banding. Compared to Jupiter and Saturn's dynamic churned atmospheres, Uranus looked almost blank. Scientists were puzzled. The leading theory now is that Uranus's internal coldness, its lack of internal heat, suppresses the convective processes that drive visible weather patterns in the other giant planets. Without heat rising from below to stir the atmosphere, Uranus sits quiet, the ice giant that keeps its feelings inside. But this apparent calm is somewhat deceptive. As Uranus has moved toward its equinox, with its equatorial regions coming into more balanced sunlight, cloud activity has increased. In recent years, Earth-based telescopes and the Hubble Space Telescope have captured increasingly dynamic cloud features on Uranus. Bright cloud bands, storms. The atmosphere is waking up, responding to the changing angle of sunlight. A planet responding to its season's decades in duration in real time. Neptune is the opposite story. Neptune is never quiet. When Voyager 2 flew past Neptune in August 1989, the last planet it would ever visit at the end of a 12-year journey, it found a planet in constant violent motion. A massive storm system, later named the Great Dark Spot, was visible comparable in relative size to Jupiter's Great Red Spot, a vast counterclockwise vortex in Neptune's southern hemisphere. Bright white clouds of methane ice streaked across the blue at high altitude, moving so fast that Voyager's cameras could track their movement over the course of hours. Wind speeds in Neptune's atmosphere were measured at approximately 2,100 kilometers per hour, the fastest sustained winds of any planet in the solar system. 2,100 kilometers per hour, sustained, not in a brief gust, as a prevailing wind. For comparison, the most powerful wind gusts ever recorded on Earth's surface came from tropical cyclone Olivia, which struck Barrow Island in Australia in April 1996, with a wind gust measured at 407 kilometers per hour. Neptune's steady prevailing winds are 5 times that speed. And here's the detail that makes Neptune's winds stranger. Still, the planet receives almost no solar energy. There is no strong temperature differential between poles and equator being driven by sunlight because there is so little sunlight to drive anything. The energy that powers those extraordinary winds comes primarily from Neptune's internal heat, a planet generating its own weather, using its own ancient warmth left over from formation to drive storms across its face in the absence of meaningful sunlight. Have you ever sat by a fire on a cold night and felt the wind that the heat itself creates the convection pulling air toward the flame? Something like that scaled to a planet, an entire gas giant generating its own atmospheric circulation from interior warmth in the near darkness 4 billion kilometers from the sun. The Great Dark Spot itself is gone now. When Hubble observed Neptune in 1994, just 5 years after Voyager's flyby, the storm had vanished. In its place, new storms had formed in the northern hemisphere. Neptune's large storms appear and dissipate on time scales of years to decades, unlike Jupiter's Great Red Spot, which has persisted for centuries. Neptune's atmosphere is dynamic in a different way. It is changeable, restless. New formations appear, old ones dissolve. The planet never settles. There is one more thing I want to share about these two distant worlds, something about how we found them, because the stories are genuinely remarkable and say something important about what human intelligence can achieve. Uranus was found by accident by observation. Neptune was found by mathematics before anyone looked through a telescope to confirm it. After Uranus was discovered in 1781, astronomers tracked its orbit carefully for decades. And something was wrong. Uranus was not following the path that Newtonian gravity predicted it should. It moved slightly ahead of its predicted position at some times and slightly behind at others. By the 1840s, two mathematicians, John Couch Adams in England and Urbain Le Verrier in France, working independently and without knowledge of each other, proposed the same solution. There must be another planet beyond Uranus. Its gravitational pull was perturbing Uranus's orbit. And by working through the mathematics, both men calculated where this unknown planet should be. Le Verrier sent his calculations to the Berlin Observatory on September 23, 1846. That same night, astronomer Johann Galle turned his telescope to the predicted position and found Neptune within 1 degree of where Le Verrier had said it would be. 1 degree. In a sky full of stars. Found on the first night of looking because mathematics said it had to be there. It was one of the greatest triumphs of theoretical physics in the 19th century. A planet discovered not with eyes but with equations. The universe for a moment did exactly what the mathematics said it would. And from Neptune's cloud tops, from that windswept, self-heated deep blue world at the edge of our solar family, if you looked back inward toward the sun, you would see it a brilliant star, brighter than any other star in the sky, bright enough in a dark sky to cast a faint shadow. But just a star, our star, the one that from Earth fills the sky with light and warmth and the possibility of blue afternoon. From Neptune, the sun is just a star among stars, a bright one, but a star. That perspective, that distance, is where our solar system ends and the true dark begins. And beyond that dark, there are other suns, other planets, other skies, skies we have never seen with any instrument, skies we have only been able to imagine until in the past 30 years, we developed just enough technology to begin to know they are real. The next worlds we visit exist beyond our sun entirely, and what their skies might look like is one of the most beautiful, most unsettling, most wonderful questions that astronomy has ever dared to ask. In 1995, a Swiss astronomer named Michel Mayor and his doctoral student Didier Queloz were working at the Haute-Provence Observatory in southern France, pointing a spectrograph at a star called 51 Pegasi, an ordinary sun-like star about 50 light-years away in the constellation Pegasus. They were looking for something that had never been confirmed before, a planet orbiting another star, not in our solar system, not around our sun, a world belonging to a completely different star, and they found one, a planet half the mass of Jupiter orbiting its star so closely that a full year on this world lasted just over 4 Earth days. A gas giant hugging its sun so tightly it would have been vaporized if it orbited any closer. They called it 51 Pegasi b. The world called it the first confirmed exoplanet orbiting a sun-like star. Mayer and Queloz called it a career-defining discovery. The Nobel Committee called it worthy of the Physics Prize in 2019, 24 years later. The universe called it the beginning of something. Since that night in 1995, we have confirmed more than 5,500 exoplanets, 5,500 worlds orbiting other stars, each one with its own sky. And the variety of those skies, the sheer improbable, staggering, humbling variety, makes everything we have seen so far on this journey look like the opening paragraph of a much longer story. Before we imagine what those skies look like, let us first address a misconception so widespread that it has become almost a cultural fixture. When people think of planets orbiting other stars, many default to imagining something roughly like our solar system. A yellow star, a family of rocky and gas planets at varying distances, perhaps one of them in a comfortable habitable zone. The assumption is that our solar system is normal, that the arrangement we live in is the template. It is not. Not even close. Our solar system is, by the standards of what we have found elsewhere, rather unusual. Most planetary systems discovered so far look nothing like ours. Many stars host multiple planets packed into orbits far tighter than Mercury's orbit around our Sun, entire solar systems that would fit inside the distance between the Sun and Earth. Many stars are red dwarfs, smaller, cooler, dimmer than our Sun, and they appear to be the most common type of star in the galaxy. Perhaps 70% or more of all stars are red dwarfs, which means that if Earth-like planets exist in habitable zones around those stars, most habitable zone planets in the galaxy are orbiting red dwarfs. And the sky above such a world would be nothing like ours. Let us go there first. A planet in the habitable zone of a red dwarf star. The habitable zone of a red dwarf is much closer to the star than Earth is to the Sun. Because red dwarfs are much cooler and dimmer, the zone where liquid water could exist on a surface is compressed inward. A planet in a red dwarf's habitable zone might orbit at a distance of just a few million kilometers compared to Earth's 150 million. At this distance, tidal locking becomes almost inevitable. The same gravitational forces that locked our moon to always show Earth the same face, the same mechanics that affect Phobos around Mars, would over time synchronize the planet's rotation with its orbit. One hemisphere would face the star permanently. The other would face permanent darkness. On the day side, a sky lit by a star that appears enormous, not because the star is large in absolute terms, but because you are so close to it. A red dwarf star seen from a tightly orbiting habitable zone planet might appear 3 to 8 times larger in the sky than our Sun appears from Earth, and its color would be different. Not the yellow-white of our Sun, which actually appears closer to white from space, but a deep, warm orange-red, like a sunrise that never ends. Like the last light of an autumn afternoon stretched across an entire hemisphere forever. The sky on the day side might be red or deep orange during the day, not blue, because the scattering of light depends on the star's spectrum, and a cooler, redder star produces less blue light to scatter. Some models suggest the dayside sky of a tidally locked planet around a red dwarf could appear salmon or amber or rust-colored, depending on atmospheric composition. The night side locked in permanent darkness would have a sky of stars, thousands of them, unmoving relative to the ground because the planet no longer rotates relative to the distant universe. The same stars would always be visible from the night side. The constellations would never change, never rise, never set. They would simply be there, always a permanent map overhead that never turned. And at the boundary, the terminator line between the eternal day and eternal night, something extraordinary. A ring of perpetual twilight circling the entire planet. A zone of permanent sunset and sunrise where the star hangs forever near the horizon, casting long shadows that never move, painting the landscape in the colors that we on Earth only see at dusk. This twilight zone might be counterintuitively the most habitable region on such a world, protected from the full blast of radiation on the day side, warmed enough to avoid the extreme cold of the night side, and bathed in a perpetual, gentle sideways light. Imagine living in permanent golden hour, every moment of every day for your entire life. Shadows always long light, always warm and low, the star always on the horizon, never overhead, never setting, just there steady and ancient, holding its position while the planet holds its breath. Now, let us visit a world that has captured the imagination of astronomers and science fiction writers alike, a real planet, confirmed that orbits 2 stars simultaneously. When the Kepler Space Telescope discovered Kepler 16b in 2011, the press release headline compared it to Tatooine, the fictional desert world in Star Wars, famous for its twin sunset. And for once, the comparison was not an exaggeration. Kepler 16b is a gas giant roughly the size of Saturn, orbiting a binary star system, 2 stars gravitationally bound to each other, orbiting their common center of mass, while the planet orbits around both of them together. The 2 stars are different from each other. One is slightly smaller and cooler than our Sun. The other is a dim red dwarf, about a fifth of the Sun's mass. They orbit each other every 41 days. And Kepler 16b orbits both of them together every 229 days. At a distance that keeps it just outside the habitable zone, it is too cold for liquid water, with surface temperatures estimated around minus 100 degrees Celsius. But from its cloud tops, from any hypothetical moon orbiting it, the sky would present something no human eye has ever witnessed directly. Two suns, not the same size, not the same color. One, a pale yellow-white, the other, a deeper orange-red. At some points in the orbit, both stars would be visible, simultaneously separated in the sky by varying distances depending on where each star is in its 41-day mutual orbit. At other times, one star would be setting while the other remained above the horizon. And at rare moments, one star would pass in front of the other, as seen from the planet, a stellar eclipse, a dimming of one sun by another, a shadow cast by starlight. The shadows on such a world would be strange. With two light sources at different positions, every object would cast two shadows, one from each star, pointing in slightly different directions, overlapping partially. Where both shadows overlap, completely absolute darkness. Where only one shadow falls, partial shadow. The landscape would be a complex pattern of light and double shadow, shifting slowly as the two stars moved relative to each other and relative to you. Since Kepler 16b, we have found additional circumbinary planets, planets orbiting two stars, Kepler 34b and Kepler 35b, announced in 2012. Kepler 47, system a binary with multiple planets, each one a real Tatooine, a place where the concept of a single sunrise needs to be replaced with something more mathematically complex and more visually extraordinary. Let us go somewhere even stranger. Let us visit a world orbiting a star so different from our sun that the physics of its sky require us to think about light itself differently. Hot Jupiters. This is the informal name for a class of exoplanet that we have found in abundance gas giants similar to Jupiter in mass, but orbiting their stars at a fraction of the distance Mercury orbits our sun. They were among the first exoplanets detected precisely because their enormous mass and extremely short orbital periods make them relatively easy to find. 51 Pegasi b was the first. Many others followed. A hot Jupiter orbiting close to its star would be tidally locked, like the red dwarf planets we discussed. Its day side would be permanently facing the star, and the temperatures on that day side with a star, sometimes similar to our sun, just a tiny fraction of the distance away, would be extraordinary. Surface temperatures on some hot Jupiters exceed 2,000 to 3,000 degrees Celsius, hotter than some stars. Hot enough that iron and silicate rock vaporize and exist in the atmosphere as gas. On these worlds, it rains iron. Silicate clouds form in the cooler night-side atmosphere, where the condensed rock particles fall as rain, and then as atmospheric circulation carries this material toward the blazing day side, it vaporizes again. A cycle of rock weather. Rain made of molten iron falling from clouds made of silicate vapor, driven by winds that move at thousands of kilometers per hour as heat tries to redistribute itself between the blasted day side and the frozen night side. The sky color on a hot Jupiter, if you were somehow suspended in its upper atmosphere, would depend on the temperature and composition. Astronomers have actually begun measuring the colors of exoplanet atmospheres using a technique called transmission spectroscopy, analyzing what wavelengths of light are absorbed as a planet passes in front of its star. In 2013, the Hubble Space Telescope determined that HD 189733ba, hot Jupiter, orbiting a star 63 light-years away, is deep blue. Not the blue of Earth's sky or Neptune's methane bands, but the blue of silicate particles scattering blue light in its upper atmosphere in much the same way dust scatters color on Mars, but in a different wavelength. A sapphire blue planet raining glass in winds of 8,700 kilometers per hour. A beautiful color, a horrifying place. I want to pause here and sit with something that I think deserves its own quiet moment. Everything we have described in this part of our journey, the red dwarf planets bathed in eternal amber light, the twin sun worlds with double shadows, the hot Jupiters raining iron. All of this was completely unknown to science 30 years ago. Before 1992, we had not confirmed a single planet outside our solar system. The concept of exoplanets existed in theory. It seemed unreasonable to assume that only our sun had planets, but we had no proof. None. In 30 years, we went from 0 confirmed exoplanets to over 5,000. The Kepler Space Telescope alone, operating from 2009 to 2018, identified over 2,600 confirmed exoplanets by watching for the tiny dimming of starlight as planets passed in front of their stars. The James Webb Space Telescope, launched in December 2021, is now capable of analyzing the atmospheric composition of exoplanets in extraordinary detail, detecting specific molecules, measuring temperature gradients, beginning to map weather patterns on worlds we will never visit. We have found planets in the habitable zones of their stars. We have found planets with water vapor in their atmospheres. We have found a planet K2-18b that some researchers believe may have an ocean beneath a hydrogen-rich atmosphere, though this remains debated. We have found planets around almost every type of star we have looked at. Planets around ancient stars 10 billion years old. Planets around very young stars still forming. Planets in globular clusters containing hundreds of thousands of stars. Planets around stellar remnants, white dwarfs, the cooling cores of dead stars. The universe, it turns out, makes planets the way it makes everything else, abundantly, continuously, in extraordinary variety. And every one of those planets has a sky, each one shaped by its star, its atmosphere, its distance, its moons, its axial tilt, its history. Each sky a unique combination of physics just as particular and precise as the blue of ours, and probably just as beautiful, in ways we may not yet have the vocabulary to describe. Here's the question I want to leave with you, not as a conclusion, but as something to carry forward somewhere out there, around one of those 5,000 confirmed worlds, or around one of the billions of unconfirmed ones. Is there a creature of some kind lying somewhere soft in the dark, looking up at its own night sky, feeling that same mixture of wonder and smallness that we feel when we look up at ours? Is there something somewhere that looks at the stars the way we do not, with instruments, not with calculation, but with the simple ancient biological impulse to look up and feel the universe looking back? We do not know. We may be a long time finding out, but the question is real. And the fact that we can ask it, that we have found enough planets, enough skies, enough evidence of a universe full of worlds, means that the question is no longer purely philosophical. It is now scientific. It is a question that data can eventually answer. Which brings us at last back to where we began, back from the binary sunsets and iron rain and amber twilight zones, back through the cold dark of Neptune's winds and Saturn's vanishing rings, back past the pink sunsets of Mars and the black noon of Mercury, back to the one sky we have always known, the one we were born under, the one that has watched over every human life that has ever been lived. And it turns out, knowing everything we now know about the skies of other worlds, the sky above our own planet is stranger, more precisely tuned, and more quietly miraculous than we ever quite gave it credit for. The last part of this journey takes us home, and home, seen clearly for the first time, is the most surprising destination of all. We have traveled a long way tonight, from Mercury's black noon sky and its impossible double sunrise, through Venus's crushing amber haze where no star has ever been seen from the surface, across Mars's pink dusty dome, where blue appears only at the wrong moment at sunset, when everything else on Earth turns red, down into Jupiter's endless falling sky with no ground waiting below, up through Saturn's ring-marked heavens, seen from the ice of Enceladus, where a hidden ocean breathes beneath your feet, out past Uranus, rolling sideways through decades of polar summer and polar night, past Neptune howling with winds 5 times stronger than any storm ever recorded on Earth, and then beyond our sun entirely, to worlds circling red dwarf stars in eternal amber twilight, to planets with 2 suns casting double shadows to gas giants, where it rains molten iron from clouds of silicate glass. We have seen a great deal of sky tonight, and now we come home. Here is something I want you to try, if you are still awake enough to try it. Not tonight necessarily, but soon. On a clear night when the sky is dark and you are somewhere away from the worst of the light pollution, go outside. Lie down if you can, on grass on a blanket on the hood of a car that is cooled. Tilt your face straight up, and just look. Not at anything in particular, just at the whole thing at once. The sky you are looking at has been studied by every human civilization that has ever existed. The Babylonians named its constellations. The ancient Egyptians aligned their pyramids to stars within it. The Polynesian navigators read it like a map across thousands of miles of open Pacific crossing from island to island without compass or instrument, guided entirely by the movement of stars whose rising and setting points they had memorized across generations. The ancient Greeks built entire philosophical systems around it. Galileo pointed a crude telescope at it in 1609 and discovered that it contained more than anyone had imagined. Edwin Hubble looked at faint smudges of light within it in the 1920s and realized those smudges were entire galaxies, billions of stars each so far away that the light reaching his eye had been traveling for millions of years. Every one of those humans looked at the same sky you are looking at right now, the same arrangement of stars, the same moon more or less, the same dark between them. And every one of them felt some version of what you feel when you look up that particular mixture of smallness and wonder, of belonging and insignificance that the night sky produces in a human nervous system with a reliability that no other experience quite matches. There is a word for this. The philosopher Immanuel Kant wrote about it in 1788 in his Critique of Practical Reason, in the famous closing lines that are among the most quoted in all of philosophy. He wrote, "Two things fill the mind with ever new and increasing admiration and awe, the more often and steadily we reflect upon them the starry sky above me and the moral law within me." He was writing about the specific feeling of looking up at the night sky and feeling it push back against you, not physically, but existentially. The feeling that the universe is real, that it is vast, and that you are somehow inside it and aware of being so. Kant never had a telescope powerful enough to see what we now know is out there. He did not know about exoplanets. He did not know the scale of the galaxy, which contains between 200 and 400 billion stars. He did not know that our galaxy is one of at least 2 trillion galaxies in the observable universe. He did not know any of that. And yet, he felt it. He felt the scale of it intuitively just from looking up. Imagine what he would feel now. Here is what I find most remarkable about the journey we have taken tonight, and I want to be precise because precision is important here, and this is not just poetry. Every single sky we visited is shaped by the same physical laws. The same equations that govern the scattering of light in Earth's atmosphere also govern the scattering of light in Mars's dust and Neptune's methane clouds. The same gravitational mathematics that describes how our moon orbits Earth also describes how Phobos races around Mars, how Titan hangs above Saturn, how Kepler 16b orbits 2 stars at once. The same nuclear physics that makes our sun shine makes every other star in the universe shine. The laws of physics do not change from planet to planet. They do not vary between solar systems. They do not care whether the atmosphere is nitrogen and oxygen, or carbon dioxide and sulfuric acid, or methane and tholins. The same rules apply everywhere, always, without exception. And from those same rules applied to different starting conditions, different distances, different compositions emerges this breathtaking variety of sky. Pink and black and blue and amber and deep red orange and electric blue and iron rain and twin sun gold. One set of rules. infinite variation. Applied across a universe containing, by current estimates, approximately 10 to the power of 24 stars. A 1 followed by 24 zeros, more stars than grains of sand on all of Earth's beaches. And around many of those stars, planets. And above those planets, skies, each one unique, each one following the same rules, each one in its own way beautiful. That thought should be almost unbearable in its scale. And yet, here we are bearing it, because we are the kind of creature that can. Now, I want to address something directly because I think it comes up genuinely for a lot of people when they spend time thinking about the vastness of the universe. It can start to feel lonely, the enormous distances, the silence between the stars, the fact that we are, as far as current evidence shows, the only beings in the known universe who have looked out at this immensity and asked what it means. We may not be alone, we do not know, but we are at the very least isolated enough that the loneliness is real and the question is real. The astronomer Carl Sagan, who spent much of his career trying to make the universe legible and emotionally accessible to ordinary people, once said something about this that I keep returning to. He said, and I am paraphrasing, not quoting directly, that the universe is not required to make sense to us. It did not arise for our benefit. It does not operate according to our preferences. And yet, it produced us. Somewhere in the ordinary workings of physics and chemistry and time, it produced creatures who can understand portions of it, who can grieve its indifference and celebrate its beauty, who can build telescopes and send probes and do mathematics that predicts where a planet should be before anyone looks for it. The universe did not do this on purpose. But it happened, and we are the result. And that particular accident, that particular improbability seems to me at least like something worth noticing, worth staying awake for, worth lying outside in the dark to appreciate. Has the scale of the universe ever made you feel lonely? Or does it make you feel something else, something harder to name? I think both are valid. I think both are honest. And I think the fact that you were here thinking about it at all is itself an answer of a kind. Let me leave you with one final fact, one real measured, verified piece of data that I have been saving for the end because I think it belongs here. The light reaching your eyes when you look at the night sky is old. Every star you see is not where it appears to be. It is where it was when the light that is now touching your eyes first left it. The nearest star beyond our sun, Proxima Centauri, is 4.24 light-years away. The light you see from it left over 4 years ago. The stars of the Orion constellation that are visible to the naked eye are hundreds of light-years away. The light from Betelgeuse, the reddish star in Orion's shoulder, has been traveling for approximately 700 years before reaching you. When that light left Betelgeuse, the Black Death had just swept through Europe. Joan of Arc had not yet been born. The printing press did not exist, and the faint smudge of the Andromeda Galaxy, visible to the naked eye, on a dark night as a faint elongated blur, the light from that smudge left 2.5 million years ago, before Homo sapiens existed, before our species had fully separated from our ancestors. The light was already on its way here before we were the kind of creature that could appreciate it. You are not looking at the sky. You are looking at the past, layered and deep. A photograph taken over millions of years arriving at your eyes in this precise moment, at this particular night, when you happen to be outside and paying attention. The night sky is a time machine, and you are standing inside it. We have visited 7 worlds and reached beyond our solar system entirely. We have seen skies made of acid cloud and iron rain of double shadows, and 42-year polar nights of black noon and pink twilight and rings that arch overhead like a bridge built by something that has no interest in being understood. And we have come home to this, to a blue sky that turns red at sunset, to one moon coincidentally perfect in size for total eclipses, to an atmosphere thin enough to breathe and thick enough to scatter light into blue, to a star close enough to warm us and far enough to let us sleep at night. The sky above Earth is not the most dramatic in the solar system. It is not the largest or the most colorful or the most extreme, but it is the one that for the entirety of human history has watched over every story we have ever told. Every love, every loss, every question, every answer, every night someone lay awake and looked up and felt the universe pressing gently against the inside of their chest. It is ours, and it is extraordinary. And tonight, I hope it looks a little different to you, a little more earned, a little more particular, a little more precious than it did when we started. Thank you, truly, for spending this time out here in the dark with me, for letting these skies sit with you for a while, for being curious enough to travel without moving, and still enough to hear what the universe has been quietly saying this whole time. If this journey meant something to you tonight, if one image stayed with you, one fact surprised you, one sky made you catch your breath, I hope you'll carry it forward. Share it with someone. Leave a comment below about which sky you found most extraordinary. Because I am genuinely curious, was it Saturn's rings arching over Enceladus, the double sunrise on Mercury, the iron rain on a hot Jupiter? Tell me. These conversations are why we do this. And if you haven't already a subscribe, the small bell that means the next quiet night can find you again, each of those things matters more than you might think. They are what allow these stories to keep being told. The next journey is already being prepared. Another question that the universe has been holding quietly waiting for us to ask. Another story told softly in the dark for anyone willing to listen. Sleep well. Dream of other skies. And remember, somewhere out there right now, under a sky, you have never seen something extraordinary is happening. Good night.